Another kind of problem that often arises is you are given two isotopes, you're given their masses, you're also given the average mass, and in other words from the periodic table, and you want to calculate the frequencies. And this kind of problem illustrates an important general idea of sometimes having to set up two simultaneous equations to solve a problem. And you'll see more examples of this if you take Chemistry 101. So from the table again, 5.2 in the chapter, the information I'm going to take tells us that there are two isotopes of chlorine, chlorine 35, and its mass is 34.96885 atomic mass units. There's also chlorine 37, that's the second isotope of chlorine, and that's 36.96590 atomic mass units. And here we're not going to tell you what the two frequencies are, which we'll call frequency A and frequency B. But what I am going to tell you is that the average mass, and this is according to the periodic chart, is 35.453. So the question here is, how do I calculate what frequencies A and frequency B actually are? So again, you set up the equation. This is always a general principle. The equation that solves this problem is the fact the average mass is the frequency of one times its mass plus the frequency of the other times its mass. And of course, this should be mass A here and times mass B. What the problem here is you have two unknowns, FA and FB, and you've only got one equation. So as you know, there is no way to solve that kind of an equation without having an independent second equation. And the independent second equation is obvious, and yet it's sometimes a little tricky to see. Don't the two frequencies, FA and FB, add up to 1? And I'm going to write this as 1.0000 just to signify this is an exact one. By definition, if there are only two isotopes, the sum of the frequencies has to equal to 1. Or in other words, the sum of the percentages has to equal 100%. So if I write that second equation, I can use the substitution method to solve. In other words, and I'm going to arbitrarily do it this way, FB would be 1 minus FA. I'm not going to bother putting the zeros after the 1, but the point is I keep in mind this is an exact 1. And so in any sig fig arithmetic, I'll treat that to be exact. Notice it's nothing wrong with solving the other way and letting FA equal 1 minus FB, but I'm doing it this way. So you have to do it one way or the other. So the average mass then, as before, would be, of course, the frequency of A times M sub A. And now what I'm going to do is substitute. Rather than write FB, I'm going to write 1 minus FA times MB. So what I'm doing here is giving myself one equation that also has just the one unknown F sub A. So if I expand terms, which is the usual procedure here, you have F sub A, M sub A, and then that will be MB minus F sub A, MB. Then I want to combine terms that contain the FA, so I can say the average mass would be MB. I'm going to rearrange slightly here, and then plus F sub A, M sub A minus F sub B, M sub B, and then factor out the F sub A, and that gives me M sub B plus F sub A times M sub A minus M sub B. And then what I'm going to do is move the FB to the other side, MB rather, to the other side, so I have the average mass minus MB equals F sub A times M sub A minus M sub B. Divide both sides by the term M sub A minus M sub B, and that gives me average mass minus MB, all divided by M sub A minus M sub B equals FA. So there's my equation for FA. And at this point, I simply plug in. Notice, and again, this I think is a very important principle, we manipulate the symbols, not the numbers. You would easily get confused here if you tried to put these long numbers in the place of these symbols F sub A and M sub A and so forth. But now it's a plug-in. So my average mass was given to me as 35.453, and the M sub B, I'm just arbitrarily calling the second isotope, that's the 37 M sub B, so that's going to be 36.96590, and that's all being divided by 34.96885, that's the M sub A, minus again the M sub B, which is 36.96590, when I do the subtractions here, and again paying attention to sig figs, the top term here is going to be to the nearest 1,000th, because the average mass that I was given to that degree of precision. So arithmetically that comes out to minus 1.513. The bottom term here is written to a higher degree of precision because I am subtracting the two given masses, which were given out to the nearest fifth place behind the decimal. So that becomes minus 1.99705. Notice, and of course you have a real problem if it doesn't work out this way. F sub a has to be a real quantity. It has to be greater than 0. But I have a minus number divided by a minus number, so of course it comes out positive, and this arithmetic comes out to 0.7576 for sig figs based on the top number of minus 1.513. So that's the frequency F sub a, which of course correlates, remember, to the first isotope, the chlorine-35, because I arbitrarily defined it that way. Of course, F sub b, the other one, is simply going to be 1, that's an exact 1, minus the 0.7576, and arithmetically that comes out to 0.2424, i.e. M sub b, I should say isotope number 2, the 37, chlorine-37, is present 24.24% of the time. The other one 75.76% of the time. And if you look at the chart, you'll see that correlates very strongly with the given data. So the idea in solving this kind of problem is simply to write out two equations, and they're always the same two equations, and then do the substitution method to solve for one of the two variables. And I've gone through this solving for F sub a. It might be worth your time to do the same procedure and solve for F sub b. Just let F sub a be 1 minus F sub b and run through the algebra, because it's always good practice. Interestingly, what you'll see is that if you do it that way, you'll end up with two positive numbers top and bottom of this fraction bar down here at the end when you're actually solving from F sub a. And of course that works too. And of course you get the number 0.2424 basically. In other words, you'd be solving for F sub b. But it's an important skill to develop, to take a chemistry problem and turn it basically into two or more sometimes simultaneous equations and solve this at this point strictly as an algebra problem.